So based on these, we try to implement few of the experiments which are related to hardware experiments. ASK is anyways there in simulation. We don't have the hardware aspect. So let us go ahead with the FSK implementation using CD4051. Now, in this case, what assumption we make is we assume that we are using two carriers with different frequency. This is the same carrier what we have discussed in the previous slides. So now here what we do is based on the select lines. Based on the select lines, we choose either of the frequencies. So here what we are doing. So we have all the select lines which are present over here. That is pin number 13 is the I0. So this is I0. This is actually equal to I1. So we'll just observe here. So here we can see pin number, this is 13 is related to I0. Pin number 14 is related to I1. Remaining are of no use for me at present. And since only two combinations, either 0 or 1. So out of these three select lines, one select line is sufficient. So other select lines, what I do is I ground it. So I require the combination like 000 and 001. So it is like only these two. Only these two I'll be referring. So when it is 000, what happens is I select I0, and when it is 001, I select I1. So this is what I'll be utilizing. So based on this logic, what we have is we can observe pin number 9. So what is pin number 9? Pin number 9 is C, pin number 10 is B. And this is pin number 11, which is the input select line A. So now here, what does this refer? This specifies that this is the least significant bit of the select line, and this is the most significant bit of the select line. So therefore, if it is 000, so if ABC, that is CAB, C is MS bit, B is the between, and A is the LS bit. So if this is the case, if it is 000, then pin number I0 is selected. And if it is 001, pin number I1 is selected. So here what we need to change, we need to just change this. So here what we do is we connect the bit stream to this pin. We connect the bit stream to input A, that is pin number 11. And these two, what we do is we connect them to ground, making it logical 0. So whenever bit is 0, I0 is selected, and whenever bit is 1, I1 is selected. So that is what we are trying to implement over here. So here we have I0, and here we have I1. And at the select line A, that is pin number 11. So this is actually a least significant bit of the select line, and this one is the most significant bit. So since they are connected to ground, they are always 0. They are always 0. And here what we have done, we have connected it to the bit string. We have connected it to the bit string. So whenever this bit is 0, whenever this bit is 0, pin number 13 will be selected, and whatever input is presented over here will be presented at the output. Will be presented at the output. And similarly, if this bit is 1, pin number 14 data is selected. So whatever data is present at pin number 14 will be presented at the output. So in this way, what we do is we check out whether the data is 0 or 1, and then send the high frequency signal or the low frequency signal. So if bit 0 is there, we are sending low frequency signal. So what we do is we connect a low frequency signal to pin number 13. And if data is 1, we send a high frequency signal. Therefore, what we do is we connect a high frequency signal to pin number 14. So, therefore, what happens is we will be getting a output of FSK at pin number 3 over here. That is, this is what we will be getting over here. Okay. So we'll be getting this waveform, that is a modulated waveform. So even in simulation, we have observed this, and in previous session also we have discussed this. So now what about the demodulation part? So this is giving you the modulation. This is giving you the modulation. Now this part gives you demodulation. This part gives you the demodulation. Now when we are demodulating, what logical aspect we look forward is we try to retain the high frequency signal and we try to suppress the low frequency signal. So how do I identify here? So if the data is high, so here you can see that if the frequency is higher in the given bit duration, so it is directly referred to logic 1. So that is indirectly what they're specifying is if the energy content in the given bit period, if the frequency is higher, we have more amount of energy which is present over here. If the energy is higher, then we detect that it is a logic 1. And here you can see that in the given bit duration, if it is a low frequency signal, so indirectly what? If the energy is below some critical value, then this will be considered as a logic 0 at the receiver end. So now in hardware implementation, what we are doing is we are this is the transmitted wave at the receiving end. What we are doing is we are assuming that coherent detection is being implemented. What we do is we suppress this low frequency content. We suppress this low frequency content so that it becomes easy for us in the next stage to detect whether it's a logic 0 or logic 1. So how do I do it? I make use of a high pass filter at the receiving end, which filters only this part, which filters the high frequency content. So here we are performing that operation. So this is actually a high pass filter. So what is this doing? So here you give the input. So it may be a high frequency signal followed with a low frequency signal. Again, it might be a high frequency signal followed with the low frequency signal. Say if this is the FSK result what we have, and this is given as input to this FSK. So when you pass it through the high pass filter, what happens is this part gets suppressed. So therefore input at this point, what it will be like only the high frequency content will be retained. And this one, we assume that it is suppressed to 0. That is, this part is suppressed to 0. And again, only the high frequency content is retained. And next, again, this part is suppressed to 0. So therefore, we get this output at the filter, high pass filter. Now, what does this look like? This is actually a kind of ASK waveform what you have. So this is actually a ASK demodulator. So you add a high pass filter and use the ASK demodulator, you get the demodulator for the FSK. So now here what this filter does is, what this demodulator circuit does is, this is the input which is applied to the diode. This is the input which is applied to the diode. So what happens is during the positive half cycle of this entire cycle, the diode is on, and because of which the DCB gets charged. DCB gets charged. So therefore, what happens is during the positive half cycle, we get waveforms which are in this way. That is only this positive half cycle will be off. And this will So, and during the negative half cycle, this is off. Therefore, what happens is this starts to discharge and it might end up with a 0 value. Again, during the next this thing, only the positive half cycle gets charged over there and this continues. Now, what is happening is if you just observe, I try to measure the energy content which is present in this time period. If it is high, then we consider it as logic 1. If it is low, we consider it as logic 0. But now what we do is But what we consider is based on the filter design and the frequency what you have chosen what you can do is, and the DCB value, that is this RC time constant. If I adjust this such a way that if the discharging is controlled, so now what we have something in this form. We are obtaining the output waveforms in this way. That is the output of the modulator. Now in this case, what we can do is if I adjust the RC time constant over here and this filter is properly designed, what I can do is I can reduce the discharging time constant and it can maintain its peak until the next value is obtained. So what this blue line what I am representing is representing the filter getting charged, that is the DCB getting charged, and when it goes to zero, right, it starts to discharge. But if RC time constant is controlled properly, then it maintains its value until you receive the next peak. So similarly, in the next this thing, and what happens is during this time period, it might get discharged completely. That is when the data is zero. So this might again continue and you might get an output waveform which is in this form. So it might be like this. So if you try to adjust it, it might be something displayed in this form. So if you observe on the CRO, it will be something in this form. So this is like in the bit period, this is like logic 1, this is logic 0, logic 1, logic 0. So you had transmitted that information and you are able to recover that information. So that is what you try to implement in FSK. Next, what we have to look out is we have to look out for PSK. So in this, what we do is, so again, this is a digital modulation technique in which we make use of the logic 1 and logic 0, that is bit streams, to modulate the carrier signal. So here we have the carrier signal. This is logic 1, logic 0. So this is a bit sequence. Now in this case, what is done is whenever data is logic 1, we transmit the carrier without changing its phase. So this is the carrier signal. So the carrier signal's phase is maintained and it is sent as it is during the entire bit interval up to this point. But whenever it is say logic 0, what is done is they have a phase inverse of 180 degrees. That is, there is a phase shift of 180 degrees with respect to this carrier signal. And the carrier signal is 180 degrees out of phase and then it is transmitted. So for example, if I am having, say this is the carrier signal and 180 degrees out of phase implies this will be in opposite form. This will be like this. So for logic 1 you send it as it is. For logic 0 you put a 180 degrees out of phase and then transmit it. So this is what you are looking forward. Okay, so this is what is happening. So now how do I implement it in hardware form? Again, I make use of the same concept. So here this is the select line, which is the LS bit, and C is the MS bit. Since these are grounded, these will always be 0 0, and we are applying bit stream to pin number 11. So it is like 0 0 0. If the bit stream is 0, I naught is selected. If the pin 11 is, that is the bit stream is 1, then I1 is selected. I1 is selected. So now based on that, pin number 13 and 14. So you try to implement this. Now in some cases what happens is for logic 1, few of the cases they send the inverted version, and for logic 0 they send it as it is. So both the logics are fine. Both the logics are fine. It is not that but you should have a inverted phase for one of the representations. If it is logic 0, you are sending it as it is. For logic 1, you send 180 degrees out of phase. Or else if you are reversing the condition, that is for logic 1, you are sending in phase. For logic 0, you send 180 degrees out of phase. So you can implement it in that form. So here, whenever data is 0, I0 is selected, and whenever data is 1, I1 is selected. That is pin number 14. Whatever input is there, that is selected. So now in this case, what we do is we consider a carrier signal, pass it through a phase inverter, which can be implemented using a op-amp. So once you phase invert that, you apply this phase inverter to one of the pins and the carrier as it is to the other pins. So based on this logic, right, either the carrier as it is without the change in the phase will be passed on to pin number 3 and I'll be getting the PSK output over here, or else pin number 14 is selected and that result will be presented to pin number 3. So this is how we obtain the PSK output. PSK output. Then apart from this, here this is nothing but the implementation of phase inversion using the op-amp. So what you're doing, you are applying C of T to pin number 2. Pin number 2 of op-amp is what? It is the inverting pin. It is the inverting pin. So whatever input you give over here, it will be inverted and presented at the output over here. And here you can see that RF, that is the feedback resistance, is 1 kilo ohm and R1 is 1 kilo ohm. So therefore what happens is gain of this amplifier is 1. So therefore you are not changing the amplitude parameter of this inverted carrier. So you are using carrier at pin number 3 over here and minus C of 3, that is the inverted version, at pin number 14. And these, after applying these, you are able to obtain the PSK output. Now what we have to do in order to get back, so this part is for modulation. This part is used for modulation. Now here we have the demodulator circuit. So for demodulator, what we have to do, first we need to identify what is the phase. First we need to identify what is the phase. So based on that phase, we try to identify whether it is logic 0 or logic 1. So this is one way of implementation. Now we are assuming that it is a coherent detection. So what we do is we make use of the carrier, and at the receiving end we uh, add this carrier with this PSK result. So when I add these two, what happens? When I add the carrier signal with the PSK output, what I'll be getting? So if I just see here, both are overlapping. So it will be like, if this is having a peak value of 2.5, this is having a peak value of 2.5. So it will be like 2.5 plus 2.5. So all the points get added in this bit interval. So from here to here, what happens? The strength of the signal will be increased. Okay, it will be increased. Now what about in this case, they are totally in opposite. So here if I start, so this is the point. So here if I start, they are in total opposite phase. So this is minus 2.5, this is plus 2.5. If this is 1, this is minus 1. So these are the points which are actually overlapping. So therefore what happens is this becomes 0. Then again in this part they are getting added, therefore their strength will be higher. So what we are doing is we are adding carrier signal and the PSK signal so that we suppress one of the part, and using the other part we try to identify what is the data. So that is what we are performing in this part. So here what we are doing is we are taking the PSK signal what we have generated and adding it with the carrier signal. So when we add that, what happens is we will be getting the addition of C of T plus the PSK signal. That is, we will be getting this waveform. This is the result of the addition. So this is adder implemented using the op-amp. So now what happens is, at this point again you can observe that you have a signal which is of this kind. So now again this is an envelope detector. What happens is, during the positive half cycle the diode is on and this charges the DCB. So when the charge is on, what happens is it charges, and when it is off, right, what happens is it tries to discharge to the 10 kilo ohm. So it tries to retain its charge. Again when during next this thing it comes. So if I consider the above waveform itself, So the capacitor charges, then it discharges, it charges, discharges, charges, discharges. Now again it is 0, so it keeps on discharging and it becomes 0. So during the entire when the bit is 0, right, when nothing is there, so it becomes 0. So again this charging and discharging process continues, and we'll be having a waveform which will be of this kind. It will be of this kind. So now what we do is, in this given bit interval, we can observe that bit is 1, and this given bit interval, bit is 0, again bit is 1 and bit is 0. So this is the demodulation with respect to PSK implementation. So this is another example what we have taken. So we try to recover the original information. So this is all for today. In the coming 4 sessions, right, we'll be discussing regarding time division multiplexing. So again, I specify these are actually related to the hardware experiments.